Newton's laws. Newton's first law of motion says that an object in motion will stay in motion and an object at rest will stay at rest unless they're acted on by an unbalanced force. Here are some points of Newton's first law. An object will not change its motion unless a force acts on it. An object that is not moving remains at rest until something pushes or pulls it. An object that is moving remains moving until something pushes or pulls it. All objects resist having their motion changed. This tendency to resist a change in motion is called inertia. The more mass an object has, the greater its inertia. Example 1 of Newton's first law. In example 1, there is a pen resting on a table. This pen would not move unless there are unbalanced forces acting on it, which makes it move. The two forces acting on this pen are force gravity and force normal. These forces are balanced, which means the force net is equal to 0. To confirm, let's calculate force gravity. To calculate force gravity, it's mass times the acceleration due to gravity. Let's say the mass of the pen is 100 grams or 0.1 kilograms, and multiply that by negative 9.8 meters per second squared, which is the acceleration due to gravity. And the force of gravity is equal to negative 0.98 newtons. So in this case, the force normal is acting in the opposite direction of force gravity. So negative multiplied by a negative is a positive. So the force normal is positive 0.98 newtons. So to go back to the force formula, force net equals to force of gravity plus force normal. The two forces cancel out because they are the same magnitude but in different directions. So the force net equals to 0. Now, what if we threw this pen in outer space? The pen would keep moving in the same direction at the same magnitude because there are no forces to stop it in outer space. Let's look at kicking the soccer ball. As this person kicks the soccer ball stops moving because it hits the goal poles. If there were no goal poles, would the soccer ball keep moving? Well, yes and no. It would keep moving, but then it would still stop because of force of gravity, which brings it down to the ground. And then the force of friction, which stops it. So unless there are goal poles in outer space, the pen would probably keep moving. Example 2 of Newton's first law. In example 2, the experiment carried out will be quite similar to the tablecloth experiment. I'll be pulling out newspaper under a bottle of oil. Let's see if the ball of oil moves. The ball of oil does move a little, but you can see it's struggling not to move. This resistance to change is called inertia, as we learned before. The forces acting on the ball of oil is the force of gravity, force of normal because it is on a surface, the force of friction, and the force applied. In the free body diagram, the force applied is greater than the force of friction because the ball of oil did move a little, but if the force of friction and the force applied were the same, then the ball of oil would not move. In this next experiment, it's going to be the same thing, but a side-by-side comparison with the ball of oil, which has greater mass, with a piece of plastic, which has less mass. The piece of plastic moves much more than the ball of oil. The reason is because the greater the mass means greater inertia, which means greater resistance to change. So the plastic with less mass has less resistance to change, so less resistance to motion, so it moves easily. Newton's second law. The second law of motion states that the force of an object is equal to its mass times its acceleration. These are some points of Newton's second law. A change in motion occurs only if a net force is exerted on an object. A net force changes the velocity of the object and causes it to accelerate. If an object is acted upon by a net force, the change in velocity will be in the direction of the net force. The acceleration of an object depends on its mass. The more mass an object has, or the more inertia it has, the harder it is to accelerate. More mass means less acceleration if the force acting on the object is the same. Example 1 of Newton's second law. In example 1, I'll be pushing a geometry box and 3 books with more or less the same force. Let's see which one moves further. The geometry box moves further. So if I were to continue pushing the geometry box, it would accelerate. And if I were to continue moving the stack of books, it would also accelerate. But the rate of acceleration would be less for the stack of books and more for the geometry box. This is because less mass means more acceleration, and more mass means less acceleration. The forces acting upon the objects is force gravity and force normal because it is on a surface, and the force applied. To compare this, if someone were to move furniture out of their house, it would accelerate much less compared to someone just moving a chair around their house, because the mass of furniture is much more than a regular chair in someone's house. Example 2 of Newton's second law. In this example, I'll be pushing a container of petroleum jelly with both hands in both directions. However, in the hand that is pushing to the right direction will have more force applied, while the hand that's pushing to the left direction will have less force applied. Let's see the motion of the object. The object moves to the right because there is a net force. As you can see from the calculations, the net force is to the right. Although I can't calculate the forces that I've applied exactly, this is a quite similar comparison. Let's say the mass is 500 grams or 0.5 kilograms, and rearrange the formula for F net for acceleration, and then acceleration is 4 meters per second squared. So if there is a net force, there is an acceleration, and the object is moving in one direction. Newton's third law of motion states that for every action, there is an equal and opposite reaction. Here are some points of Newton's third law. When one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first object. The force exerted by the first object is the action force. The force exerted by the second object is the reaction force. Example 1 of Newton's third law. In example 1, I will apply a force downwards to the mattress on the object. Let's see what happens to the object's motion. The object bounces back. Let's take a look at the free body diagram. The initial free body diagram is the force of gravity and also the force applied, acting downwards, and the reaction force of the mattress. The action force is essentially the force applied, and so the force of the mattress is equal to the force applied. However, due to the force of gravity, the object doesn't bounce back to the same height as the height it was launched from at the force applied. And then when it stops moving, there is only force of gravity and the force normal because it is on a surface, which are also action-reaction forces. Example 2 of Newton's third law. In this example, let's say I had a balloon full of air, and then I cut off the bottom part which tied the balloon together. Then the air would act downwards. That is the action force. And then the balloon would fly upwards. That is the reaction force. These two forces act in the same magnitude but different directions, or opposite directions. That is all of Newton's laws.